Industrial environments are defined by mass, velocity, and power. The danger in a modern factory is purely mechanical, crushing weights and continuous motion. We classify these acute physical threats, like moving gears, localized fires, or sudden explosions, as safety hazards. They are immediate, highly visible, and linked directly to the materials at hand. Health hazards, however, operate on a different timeline. These are chronic, invisible threats, tied specifically to the prolonged exposure of toxic substances. In the early days of mass production, these respiratory environments were completely unregulated. Workers operated shoulder to shoulder in atmospheres saturated with raw particulates and chemical off-gassing. This presents a persistent engineering problem. Industrial processing fundamentally requires the use of toxic substances, meaning absolute zero exposure for workers is physically impossible. Instead, we rely on a foundational principle of toxicology. No substance is entirely lethal in a small enough dose, and all substances become lethal if the dose is high enough. Since elimination isn't an option, industrial survival depends entirely on strict mathematical frameworks that govern exactly how much exposure the human body can withstand. To calculate those limits, engineers have to map out exactly how different chemicals attack the human body. We approach physiology like a structural blueprint, looking for specific vulnerabilities. The first category of hazard targets the surface layer. Irritants cause immediate, localized inflammation when they contact the skin or the lungs. Ammonia gas, for example, mixes directly with the moisture on human mucous membranes to form ammonium hydroxide, a highly caustic agent that burns the respiratory tract. Irritants can also be physical solids. Prolonged inhalation of industrial dusts like iron, tin, or silica causes a scarring condition called pneumoconiosis, which permanently stiffens lung tissue. If a toxin bypasses that localized surface damage, it acts as a systemic poison. These substances absorb into the bloodstream and attack vital internal organs directly. Lead targets the digestive system and brain, while heavy metals like mercury and cadmium specifically attack the filtration systems of the kidneys and liver. A third category, depressants, targets the central nervous system. Common industrial solvents like benzene act as temporary narcotics, causing disorientation that can lead to catastrophic mechanical accidents. Finally, there are asphyxiants. Simple asphyxiants, like excess carbon dioxide, physically crowd the oxygen out of a room. Chemical asphyxiants, like carbon monoxide, do their crowding internally, bonding to hemoglobin and blocking oxygenation at the cellular level. Treating fumes as a generic hazard is a failure of industrial design. Effective protection requires mapping the specific physiological attack vector of the exact chemical in use. Once the physiological threat is mapped, safety engineers determine the physical state of the chemical to understand how it travels through the workspace. Airborne contaminants travel in 4 main vectors: gases that mix freely in the air, vapors off-gassing from liquids, mists of suspended liquid droplets, and solid particulate dusts. Knowing how a toxin attacks and how it travels sets up the core regulatory question: how do you define a mathematically safe concentration of that vector in the air? The baseline metric for this is the threshold limit value, or TLV, shown here. The TLV is a specific numeric concentration, usually measured in parts per million or milligrams per cubic meter. It represents the maximum level of a substance that a worker can be exposed to for an entire workday without experiencing significant harm. While the TLV is an industry-recommended baseline, the Occupational Safety and Health Administration enforces a legally binding parallel standard known as the Permissible Exposure Limit, or PEL. Identifying the state of the substance and locating its assigned PEL effectively turns industrial health from an abstract biological concept into a solvable algebraic equation. Real-world factory exposure is rarely a constant stream. It fluctuates continuously as workers change locations, ventilation systems cycle, and manufacturing batches process. To normalize these fluctuations, engineers use the formula for time-weighted averages you see on this dashboard. This calculates an equivalent concentration averaged over a standard 8-hour shift. Let's trace a case study. We track a worker through a single 8-hour shift, broken into 5 distinct periods. For the first 2 hours, the exposure sits at a baseline of 1.5 parts per million. For the next 2.5 hours, it spikes to 4 parts per million as an active process runs. A concentrated transfer process causes an extreme spike to 7 parts per million for 1 hour, before dropping to 5 parts per million for the next 2 hours. During the final hour of the shift, the level settles at 3 parts per million. To calculate the total exposure, we multiply each concentration level by its specific time duration. Summing those 5 values together gives us a total load of 33. We divide that sum by the standard 8-hour baseline. The result is an equivalent, normalized, time-weighted average of 4.125 parts per million. This calculation prevents short, dangerous spikes from being hidden within an otherwise clean shift. It gives safety managers a precise mathematical average to compare directly against the legal limit. Single chemical exposures are straightforward, but modern manufacturing usually involves overlapping processes. What happens to the math when a worker breathes a combination of different toxins simultaneously? To account for combined toxic loads, we use the equivalent ratio formula for mixtures shown here. The regulatory rule is absolute. Calculate the fractional exposure for each chemical, add them together, and if the total equivalent ratio exceeds 1.0, the environment is strictly non-compliant. Consider a workplace environment containing a mixture of nitric, sulfuric, and acetic acids. The air contains a nitric acid concentration of 4 against a legal limit of 5. It passes the individual safety test. Sulfuric acid sits at 0.9 against a limit of 1, and acetic acid measures 22 against a limit of 25. Evaluated individually, every chemical is legally compliant. However, when we sum the actual burden on the body, 4/5 plus 9/10 plus 22/25, the total equivalent ratio hits 2.58. Despite every individual chemical passing the regulatory test on its own, their combined biological load creates an environment nearly 3 times the legal limit. All of these mathematical frameworks fail entirely if engineers cannot accurately measure the physical concentration of odorless gases in the actual room. Historically, detecting these invisible threats relied on crude biological indicators. Miners famously carried caged canaries into shafts, relying on the bird's high respiration rate to signal a drop in oxygen or a rise in toxic gas. They also used tools like the flame safety lamp. If the proportion of oxygen in the atmosphere dropped too low, the flame would simply extinguish, providing a binary, and often too late, warning. Modern industrial compliance requires continuous measurement down to the parts per million, demanding tools far more sophisticated than animals or open flames. Today, safety personnel use precision sampling equipment like the gas detector tubes seen here for rapid, on-site atmospheric assessments. These tubes contain specialized chemical reagents designed to react explicitly with suspected contaminants. As a known volume of air is drawn through, the reagent changes color along a printed scale, providing a direct, visual readout of the concentration. These instruments form the necessary bridge between human sensory limitations and the strict mathematical requirements of occupational exposure limits. Once a facility's mathematical limits and physical measurements are verified, that baseline risk must be instantly communicable to the workers handling the materials. This is achieved through universal standardized systems, primarily the National Fire Protection Association hazard diamond displayed here. The diamond aggregates complex safety data into 4 distinct color-coded quadrants: blue for health hazards, red for flammability, yellow for reactivity, and white for specific handling instructions. The severity within these quadrants is graded on a numbered scale. A 0 indicates essentially no hazard, while a 4 indicates extreme immediate danger. A level 4 rating in the blue quadrant immediately flags the presence of the severe irritants, systemic poisons, or chemical asphyxiants that require stringent exposure calculations. Industrial hygiene is the rigorous application of physiology, mathematics, and precise instrumentation. It ensures the necessary toxic byproducts of modern manufacturing do not compromise the human operator.